Alright, hello everyone. Today, inshallah, I'll be going over Polarity, which is a small section in chapter 1, Chem 1. Bismillah. Now, just to start off, we obviously need to know what exactly is a polar covalent bond. So, a polar covalent bond is simply a covalent bond, but instead of the electrons being shared equally, they're going to be unequally shared. What do we mean by that? Basically, the electrons will actually be more attracted to the more electronegative element. Now, what do we mean by more electronegative? Electronegativity is the ability of an atom to attract electrons. And if something is more electronegative, it's going to have a greater ability or a stronger attraction to these electrons compared to the other element. Now, if you want to use it in like a real life example, it's like you're playing tug of war. You got somebody who's weak, which is the less electronegative element, and then you have a guy with muscles on the other side, which is the more electronegative element. Obviously, who's going to be able to pull the rope more? The guy with muscles. So this is basically the general idea of like the polar covalent bond. All right, now we use an arrow to show which one is more electronegative than the other. And this is how it looks like basically. You have a side that's similar to a plus sign, and then you have an arrowhead. The one that's similar to a plus sign, whatever element is here, this tells you that the element here is the less electronegative between said two elements. And the one that's here is the more electronegative between said two elements. So what does an arrow tell us? Arrow tells us the direction. So if it's pointing this way, then it's telling me that the electrons are closer to this side. All right? Now, this table is a general overview of the common elements for electronegativity. All right. Now, the numbers you're not expected to memorize them. What you're expected to know as general information is the fact that fluorine is the most electronegative element and that the value of fluorine is 4. That's all you have to know. Now, you may be like, okay, you're telling me not to memorize the numbers, but what if they don't give me the numbers and I need to know if a molecule is polar or not, or if a bond is polar or not? It's really simple actually, you just need to know these. These two phrases will help you a lot, which is the trend of electronegativity in a periodic table. Basically, the first one states that, that going from left to right, my electronegativity increases. Can we see that here? Yes, see? I'm going from here to here. We started at 1, we went to 4. We started at 0.9, we went to 3.2, 0.8, 3. Right? So we just fact check that. My second trend is that when I'm going from top to bottom, my electronegativity is actually decreasing. Now let's see if that's true. We started at 2.2, we ended with 0.8. Is it decreasing? Yes. Let's go here, for example. We started at 4, and then we ended up with 2.7. Simple as that, straightforward, and we just fact-checked the second trend. So these two trends will help you when solving and when they don't give you any numbers with it, okay? Now, let's take these for example. How do we apply the rules? Now let's look at N and O. If we see N and O, right, N and O are compared to the carbon. So here we have our carbon, and then here we have N and O. Logically speaking here, we can't use the top to bottom one because they're not in the same group, N and O, right? Exactly. So, and they're not in the same group with the carbon. See? This is a different group and this is a different group, right? So, again, let's go back to this one. What does it say? When we're going from left to right, electronegativity increases. So therefore, how is our arrow going to look like? Our arrow is going to look like this. All right, done. Then, let's go to the other one. Now we go to Cl and Br. Same thing. Where's Cl? And here's Br. Compared to carbon, are they in the same group as carbon? No. So again, we cannot use the second rule. What are we going to use? The first rule. They are more to the right compared to carbon, therefore they are more electronegative than carbon, so how is our arrow going to look like? This. Alright? Let's go to H, hydrogen. Where's my oxygen? Where's my sulfur? Here's my oxygen. Here's my sulfur. Where's my H? My H is all the way over here. Now here, H, yeah, so obviously my oxygen and my sulfur are not in the same group as my hydrogen. Logic sense. But we're going again from where? From left to right. So therefore my electronegativity is increasing or decreasing? Increasing. So my arrow is going to look like this. Now, obviously, if I wrote OH like this, my arrow isn't going to look like this. It's going to look like this. And this is just the way I wrote it, basically. Now let's go to this one. Br and Cl. Br and Cl are in the same group. Here's Cl, here's Br. So in this case, we don't use the first rule. We actually use the second rule, which is from top to bottom, where electronegativity decreases. So I have Br, which is my more electronegative, and compared to my Br, which is less electronegative than my Cl. Therefore, my arrow here would be like this. And let's go for Si and and Cl. My Si is right here, and my Cl is right here. Now again, this one we don't use the second rule. Now we go back to my first rule, which is going from left to right. And when I see that my Cl is more electronegative, right, than my Si, so how is my arrow going to look like? This. So this was just bonds. Now polarity, we can talk about it in the bond aspect and in the molecule aspect. When we're talking about the bond aspect, we're just talking about this. It's the charge distribution between two atoms, and it's unequal. When we say there's a polar bond, but when we say a polar molecule, it means the charge distribution around the whole molecule is not symmetric. On the topic of molecule polarity, when we're looking at a molecule, we need to take three factors into consideration, which are symmetry, electronegativity, and my lone pairs. Now, if a molecule, this really is the most important one. It usually tells you if it's nonpolar or polar. What do I mean by symmetry? Basically, if you have a central atom and whatever is bonded to it, whether it's 3, 2, 4, if they're all the same atom, then it's nonpolar. But if they're not, then we have to look into factors 2 and 3. Now let's look at an example. Some examples here. For example, here, right? What do I see here? Symmetrical. I have an oxygen here and an oxygen here. So directly I can say the molecule is nonpolar right off the bat. I don't even need to draw it out or anything. But how's the bond polarity going to look like? This one is directly only based on electronegativity, which we go back to using the two trends I stated here. Now, in my second case in linear polarity, this is a very, 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 very specific case, right? You don't really have much polar linear molecules, but for the cases that we do, which is, for example, here HCN, we know that carbon is more electronegative than H, so my polarity is my arrow is gonna point this way. And then we know that nitrogen is more electronegative than carbon, so again, my arrow is gonna point this way. So as you can see, the overall arrow is going to be pointing this way. Therefore, my molecule is polar, and my bonds are polar. All right. So this is for the linear cases. So for the linear case, you're either going to have a polar one or a non-polar one. Now if you go to my bent case, is when I have two lone pairs and two bonding pairs. Now, we have to take into consideration the fact that lone pairs cause a great off-balance in dipole moment, okay? So here we have these two, and then I have my two lone pairs. In the case of bent, the molecule is always, always, always going to be polar. And for my bond polarity, as you can see, there is a difference in electronegativity. Therefore, my bond is also polar. All right, so these are for the first three cases. Let's go to my trigonal planars. I have two cases of my trigonal planar. Again, what did I say we first look at? Symmetry. What can I see? 3 chlorine atoms. So therefore, right away, what can I say? My molecule is not polar. Bond polarity. Can I see a difference between bromine and chlorine? Sorry, boron and chlorine. Here's my boron. Here's my chlorine. Chlorine is obviously way more electronegative. Therefore, my arrows are going to look like this, and last but not least, like this. Right? Going to this is my second case of trigonal planar. It's more rare than the other one, but again, in the case that you do have one of them that is not the same as the other two, what did we say? If it's not symmetrical, it's polar. Okay? Again, these are one of the you don't really get asked about this one, but in case you do see a trigonal planar or a central atom with 3 bonds and one of them is different, it's a polar molecule. Now, for the case of my trigonal pyramidal, who comes back as the main star of the show? The lone pairs. Now, here in general, if we see my nitrogen is more electronegative than my hydrogen, so they're always going to point this way, and this way, and this way. There's no force going the opposite way. And if there's no force going the opposite way, then my dipole moment is going to be facing this way. And if it's going to be facing this way, what does it mean? If I have a dipole moment, it means my molecule is polar. Now, what about my bond polarity? Can I see a difference in electronegativity? Yes. Therefore, this is also polar. Now, for my last two examples, for my tetrahedral, see, it's either going to be symmetrical or asymmetrical. See how I have F, 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 F. That means I can directly say right away, non-polar. Are my bonds also polar? Yes. Why? Fluorine is more electronegative than chlorine. Fluorine is more electronegative than chlorine. Fluorine is also in this one. So therefore, my bonds are also polar. Now let's go to my asymmetrical one. In this case, my hydrogen, again, we know that hydrogen is less electronegative than carbon. And then we have my fluorine, which is the most electronegative. They're all pointing upwards. My final dipole moment is going to look like this. So therefore, what can I say about my molecule? If it's asymmetrical, polar. And for my bond polarity, they are also polar.